Hello everyone, welcome back. I hope you watched the last 5 tutorials in this series on statistical analysis in Python, where we went through the basics of statistics, descriptive statistics, comparing two groups like using, let's say, parametric tests. And in the last one, we looked at how to compare two groups using non-parametric tests, which is basically when you have your data that's non-normal distributed, or the variances are not equal, and a few other rules. If you haven't watched that, please stop this, go ahead and watch those, and then come back here. And since you're already stopping the video, or it's a good time to pause right now to hit the subscribe button, and while you are there, look at the little thanks button if you're feeling extra generous. Okay, jumping into today's topic, we are going to compare multiple groups using ANOVA. And until now, the last couple of tutorials, we looked at two groups, comparing two groups using t-test, for example, or using paired t-test if the two groups are paired before and after, using u-test in the last tutorial if it's non-parametric, right? And so on. But now, let's say we have multiple groups, not just two. And in fact, recently I published, along with obviously a few others, a paper where we looked at, various tissues in a TMA, and how these tissues, certain metrics are related between these multiple tissues, each tissue representing a different cancer stage. Let's say stage 0, 1, 2, and so on. And then you have these multiple stages, like how do you compare this data? In fact, I think ANOVA, or comparing multiple groups, is probably one of the most used statistical tests to compare data sets, because most of the time we work with multiple groups. Okay, a long introduction, but let's go ahead and jump in. And what is the plan for today's tutorial? Again, going through a quick overview and then jumping into the Python code. Please pay some attention to this first part and not just go to Python, because if it's just Python, you can just use, for example, just go to ChatGPT and ask from scipy.stats, what is the library that gives you a specific test, and then you can go ahead and use it. But when you have your data, and obviously you cannot feed the entire data to ChatGPT. I recommend not doing that, because data is precious and don't give it to anyone. You have to analyze it first. You have to check for normalcy. You have to check for variance, and you have to check for many of these tests, and then identify what test is appropriate for your specific data. And that's the type of information I'm trying to provide via these tutorials, right? So that's the basic background right there. So with that information, let's go ahead and look at the data set we're going to use. This is a new data set in this series. I think I have used the wine quality in the past. I've used the heart disease data set, but here we're going to use the Palmer Penguins data set, because here we have three groups, 3 penguin species: Adelie, Chinstrap, and Gen 2, and then they are from 3 different islands. I don't know where, probably New Zealand or Chile, definitely around Antarctica. These are penguins. And the key measurements here are body mass, their bill length, bill depth, and flipper length. And there are 344 observations with all this data. And this is, of course, a real world data collected by Dr. Christian Gorman. And this is definitely perfect for demonstrating these type of tests. Now, why ANOVA instead of multiple tests, right? So, I mean, if you have, let's say, 3 groups or 4 groups or 5 groups, you could have done group A and B, group A and C, group B and C, and so on. Well, you can do that, but then if you have 4 groups, then you have 6 pairwise comparisons. If you have 5 groups, then you have 10 of these comparisons, which is basically k times k minus 1 over 2. That many comparisons of these groups. Okay, that's one problem, but the bigger problem is there is a type 1 error inflation, right? So when you do t-test, your alpha, let's say, is 0.05, 5% chance of false positives. That's what type 1 is, false positives. If you perform multiple tests, then that can propagate. For example, with 3 groups, you may have a 14% chance of at least having one false positive, and this compounds when you have multiple groups. So ANOVA controls this family-wise error rate at an alpha of 0.05. So that's another reason why you need to consider ANOVA tests. Okay, now before jumping into how ANOVA works and getting into the details, first of all, let's look at the logic at a very high level. These are certain, let's say, facts. One is, first of all, the core question is, do the group means differ more than what we would expect by random chance alone, right? So that's our test. So the core question is, you have three different groups. Do the means differ between them than the random chance alone is the question. Now, a couple of points to consider is variance decomposition in our data. So the total variance, again, standard deviation variance, right? So how the dispersion, the spread of our data. The total variance can be split as between group variance. You have multiple groups. So you have variance between these groups, and also within the group variance. Within a given group, you have some variance spread in your data. So the total variance is between plus within the group variance. And between the group variance, I just mentioned how much group differs by each other, and within the group is how much within the group. Now, F ratio compares the two. F is nothing but your between group variance divided by within group variance. Okay? What does that mean? If you have large F, that means groups differ substantially relative to individual variation, right? And opposite for small f. Just consider this so far, okay? They will come into play later on when we jump a bit deep into ANOVA. So how does ANOVA work? First step, we compute the group means and the grand mean. We just talked about it. So we can add them within the group mean and the grand mean of all the data. Calculate the sum of squares and then convert to mean squares and compute the F statistic and compare to the critical value. Critical value is, let's say, 0.05. Here, if you like equations, here it is, right? Let's say you have three groups, A, B, and C. Step one is mean of each group, mean of A, mean of B, mean of C, and then the grand mean. Put all of the data together and get the grand mean. And then calculate SST, SSB, and SSW. These are common acronyms that we use in statistics, especially obviously in ANOVA. So calculate the sum of squares. Like total sum of squares is individual point minus the grand whole squared, and then add all of those for each data point. Between group sum of squares, go ahead and do that. And then within group sum of squares. And again, the assumption from the second slide I showed you was that SST, sum of squares, total variance, is nothing but between the group variance plus within the group variance. This is why we calculate these. The next step is to convert to mean squares. Once you have SSB and SSW, you go ahead and do mean squared between is nothing but SSB divided by k minus 1. K is basically the number of groups, and SSW is n minus k. Yeah, total number of observations. And then the F statistic is given by, we already looked at this, MSB over MSW, right? Between divided by within. And if this value is less than, compare this to a critical value, let's compute P. And if it's less than 0.05 P value, then we conclude that not all group means are equal. If you're like me, you want to walk through certain example, which we'll do in a minute. But before jumping in there, let's go ahead and look at the assumptions. When can you use ANOVA? Like any or statistical test, there are certain assumptions. One is that independence, observations are independent of each other. They're not dependent. And normality, the residuals are normally distributed. Again, we can use Shapiro-Wilk test, for example, and QQ plot to visually look at it. Homogeneity of variance, equal variances across the groups. And again, we can use Levin's test. And I say again, because we did this in the last tutorial. And of course, no extreme outliers, and outliers can affect results. So you can look at the box plots, you can look at the standardized residuals, you can look at IQRs and look at which basically box plot summarizes, and then get an idea of the outliers. And when these assumptions are violated, well, non-normality, for example, ANOVA is kind of robust if you have large samples. What do we mean by large? Greater than 30 per group, which means at least 90 in your 3-class system, right? Or 3-group system. Unequal variances, if the variances are not equal, then use Welch's ANOVA, which is basically a non-parametric alternative for this ANOVA. And extreme outliers, consider transforming your data and then working on that if you have extreme outliers. Okay, now let's go ahead and do a workout example. Again, we are going to jump into our code to look at the actual data, but when you work this out by hand, I think it makes more sense, and then you can use Python for large data. Okay, so the goal is to test whether mean cholesterol levels differ across 3 chest pain types. There are 3 chest pain types, let's say type 1, type 2, and type 3. And different patients. And for each patient, you have a cholesterol level. Obviously, this is synthetic data, so I have like mean of 200 for this type 1, mean of 250 for this type 2, mean of 230, I guess, for this type 3. Okay, makes it easy for us to follow this. Okay, well, I should have showed you this. Step 1 is group means. We know the group means. Step 2 is grand mean of all the data. You put all the data together. We have 9 data points. The grand mean is 226.67. And step 3 is calculate the sum of squares. And again, from each data point, 200 minus the grand mean, which is 226.67, and then 210 minus that, squared plus all the way, and then you get 4,250 when you do that. Okay. Part B of the step 3 is between group sum of squares. This is SST, total sum of squares. Between group, so you take group 1, obviously the mean of group 1 is 200, mean of group 2 is 250, mean of group 3 is 230, and then this is what we mean by between group sum of squares. And we get certain values and add those, you get 3,800 here. And finally, within group sum of squares, from our initial assumption, SSW equals to SST minus SSB, or SST equals to SSW plus SSB, right? So we know that within group sum of squares is this minus that, so we can get 450 right there. Okay, so we have all these values. Now, step 4 is calculating the mean squares. So SSB divided by k minus 1, SSW divided by n minus k, and you get these values right there. And F-statistic is basically this divided by that, 1900 divided by 75, which is 25.33. And you compare that to a critical value, or in this case, I am computing the p-values. I'm using just Python right there. And it's very easy from scipy.stats, import f, which calculates which gives you the p-values right there. So the input here is your F-statistic, which is 25.33, and the degrees of freedom for the first data right there, which is the numerator, df1, that's what I mean. K minus 1, 3 minus 1, which is 2, and here denominator 9 minus 3, n minus k, and that's 6. When you plug those into the p-value, you get a value of 0.0012. So we say, hey, there is a statistical difference in cholesterol levels across the 3 chest pain types. I hope that makes sense. And the next step is just using Python. Now, before jumping in, effect sizes of ANOVA. We saw Cohen's d effect when we did the t-test, for example. Similarly, here, you can use eta squared, for example, so which is nothing but SSB over SST. So in our case, that comes up to be 0.894. And the effect is very large compared to, I mean, the metrics right there. I mean, if it's 0.01, it's small, 0.14 large, and in this case, it's very large effect. And omega squared, again, you have a different equation right there, still very large effect, and partial eta squared. You can use any of these or all of these to actually compare the effect sizes. Okay, now, one thing, there is something called post-hoc testing. For example, we have 3 groups, right? We have the values of 3 different type of chest pains, Again, here, if you want to know the names, typical angina, asymptomatic, and non-anginal pain. These are the 3 types. And then I have chest pain types. The values right there, right? So 220, 230, 210, and so on. And okay, that's fine. We have these 3. And we performed an ANOVA test, and we got an F statistic of whatever, and then we say p-value, and we concluded that, okay, there is a statistical significant difference between at least one pair of groups. This is the point I'm trying to make. When you compare multiple groups, ANOVA test tells you that there is a difference between at least a pair of groups. The question is, which groups differ? That's exactly when post-hoc testing is needed, because ANOVA doesn't tell you which groups actually differ. It tells you that there is a difference, and it quantifies it, and it tells you that, hey, there is a nice high confidence that the values are, the groups are different. But now the next question is which groups? That's a natural next question. This is exactly when you perform post-hoc testing. And there are 2 types of tests that I'm going to talk about. Tukey's honestly significant difference, HSD test, and it compares all group pairs while controlling the family-wise error rate, false positive rate due to multiple comparisons that I talked about earlier. And of course, the assumption here is equal variances are assumed. If there is no equal variance, there is another test that I'm going to talk about in a second, but let's focus on Tukey's honestly HSD test. It's typically called HSD test. And let's look at the same data. You have the values of 220, 230, 210 for typical asymptomatic and non-anginal chest pain. And step 1 is calculate group means and sample size. Yeah, let's call A as the first one, typical, B as asymptomatic, and C as non-anginal. If that's the case, basically we are calculating averages right there. And each group has 3 data points, so there you go. And step 2 is get mean square. We just did MSW calculation a couple of slides ago, and we got a value of 75, right? In case you forgot. Oh, that's a long ways ago. A value of 75 right here. Okay, all I'm doing is I'm just taking that value and using that here. I promise not to go back then. There's too much animation going on. Okay, so that's step 2. Step 3 is use the HSD formula, which is Q multiplied by square root of MSW over N. Q is studentized range statistic. What the heck does that mean? We'll get to that in a second. And MSW, we know what that is. N is, we know what that is. We have 3 data points, right? So 3. MSW is 75. How did I get this 4.34? Well, now we have to look at a lookup table. The Q based on how many number of groups do we have? What is the degrees of freedom within? And for what alpha? 0.05. Okay, I added a link here. Okay, and if you follow the link, you'll see a page like this, and you see alpha 0.10 or alpha is 0.05, and we have 3, k equals to 3, and degrees of freedom 6. If you look at that, you get a value of 4.339, and this is exactly what you see right there, 4.34, yeah, from the tables, and you plug that in and you get a value of 21.7, and then you look at each of these, compare mean differences to HSD. Like A versus B, it's 85. Because A mean is 305, B is 220, so it's 85, 25, 60, and you compare that to the HSD and you say, is this significant difference? Yes, yes, and yes. In this case, in our case, A and B, A and C, and B and C, they all differ from each other. This is basically Tukey's HSD test. Next, let's look at KW test, Kruskal-Wallis test. This is for non-parametric, which basically means it just compares the ranks instead of the raw values, and it doesn't assume normality because it's just looking at the ranks. It doesn't assume normality or equal variances. The way it works is, again, going back to the same data set. Now you compile all data and rank it. So we have values to 10 to 30 to 20, 300, blah, 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 whatever. You arrange them and you rank them. 210 is the smallest, 310 is the largest. And these are all, again, the way I gave the values, they kind of fall into AAA, CCC, BBB, but obviously in reality, these can be mixed, but you give certain ranks to them. And then step 2 is sum of ranks per group. For A, it's 1 plus 2 plus 3. For B, it's 7 plus 8 plus 9, and so on. And then each group, the NI number of data points is 3, so total is 9. So far, so good. The next step is use the Kruskal-Wallis formula, and here is the formula: 12 divided by n times n plus 1. Now, if you ask the question, where did you get the formula? That's when you open up the statistics textbook and kind of read what's going on there, okay? That's way too deep, and I don't pretend that I know why this is. When I took the statistics class, I bet this was part of my coursework. I totally forgot. But I know that this is the equation, and we have all the values to plug in, basically. And then you get a value of 7.2. And step 4 is to compare to chi-squared critical value. So we have degrees of freedom right there. And from chi-squared table, again, critical value at alpha 0.05 is 5.99. Again, another table, it's 5.99. And we got a value of 7.2 and H greater than that, which means there is a significant difference. And there you go. Okay, so finally, step-by-step ANOVA process. All I'm doing here is showing you screenshots of our Colab notebook where we will look at these. And there are various plots, as you can see. And here you can see, the statistics and ANOVA. And step 2 is check the assumptions. This is very important. Is it normal? Is the variance homogeneous? And also detect the outliers. And then the next step is, okay, then go ahead and perform the ANOVA test, one-way test. There's also two-way. I'm not going to get into that yet, probably in later tutorials. This is one-way test. And there you go, corresponding plots. And of course, power analysis for ANOVA if you just want to look at. And I covered power analysis not in the last one, but in the one before that where I talked about t-tests. And please look at that. And this is 80% power is achieved at Cohen's, at this value. With a total number of, for example, 60, you get 80% power at this specific value. Again, go ahead and check 2 videos prior to this one. And also Tukey's post-hoc, I'm just checking if there is anything to talk about, because all of that, we'll see that in the code. So why not just jump to the code right away? Okay, so as usual, our imports are at the top, and they should be familiar to you. Again, if you have watched the last few tutorials, we have pandas, numpy, matplotlib for plotting, cborn for plotting, scipy.stats again is something we are using quite regularly, and in this case from stats.models like scipy.stats. I don't know if it has ANOVA. Probably does. Statsmodels.formula.api and .ANOVA.multicomp pairwise Tukey. There's a reason I'm using stats models. I believe I looked for Tukey's HSD test in scipy.stats and I couldn't find it. So I'm like, hey, let's switch the libraries to stats models. So this is another common one that at least I use quite often. Within stats models, you can actually find the power and all the other tools. Okay, let's go ahead and run this. And the data set, let's go ahead and get the Penguin dataset right there. You can download it. Just Google search for Palmer Penguin dataset. You'll find it from probably UCI resource like right there, and download the zip file and read the CSV file, or you can directly get it from this specific URL. If the URL doesn't work, go ahead and do the alternate method, but let's check if it's working. Yeah, successfully, that's fine. And display the basic information. And again, looking at the top, looking if there is any null. I don't think this should have null. If so, we are going to drop the null values in this case. We're not going to fill with any median or any values. Although I do think there are no non-null right there. So there's nothing to worry about right there. Good. Although I don't know what that is, not a number value right there. And oh, there are some missing values, sorry. Here build length 2, 2, 6 is 11. So okay, after removing the missing values, we have 333, still okay, I guess. And let's go ahead and describe. Again, this is descriptive statistics. It tells you the mean, standard deviation, and various percentiles. Go ahead and look at that. And now let's just check a few more things. So these are different species, and we have numbers for each species. We only have 68 data points for chinstrap, but we have almost okay for these two. And these are the different islands they came from. And we have 168 male, 165 female, almost obviously equally distributed right there. And now a lot of text about ANOVA. Most of the stuff I probably copied from my PowerPoint presentation. Okay, now let's go ahead and explore the data. The step one for any data analysis, you just explore the data and then you go ahead and check for normality and all that stuff. So let's go ahead and perform some descriptive statistics, some plots. I don't think it needs any explanation. Most of the time it's either looking for means or maximum and plotting those, and visualization, right? Box plot, violin plot. Again, this is a bunch of code that you can use on your own data sets, and QQ plots, for example, to see how normal the data is. And I think I'm doing a bit more. Effect size preview, calculate between group sum of squares, and then SSW, eta squared, calculate all the stuff that we just discussed in the PowerPoint presentation. We are actually getting all that information here printed. So let's go ahead and look at it a little bit and then move on to the next part. So descriptive statistics by species. So for each of these data sets this is like a nice project, right? It can take hours for you to just sit and look at the data. Obviously, this one is different when it comes to body mass compared to these two groups. You can visually tell that. You can visually tell that right here. These two are almost identical, right? So these two are identical. I don't see much of a difference between them, between the Adelie and chinstrap species, but this Gen 2 species is much different. This one looks almost normal distributed, but again, we'll check. Total sum of squares. Okay, so that's it. Now let's go ahead and look at ANOVA assumptions. Do the assumptions hold good? And we know what those are, right? So we look at the residuals, for example, and we'll use simplest approach like value minus group mean. I mean, we discussed all of this as part of our tutorials again. And I'm checking normality. You have to check that first. And multiple ways. QQ plot, histogram of residuals is another one. And we are kind of overlaying that. And homogeneity of variance, we are just looking at those plots, and box plot. And Cook's distance, outlier. I mean, this is one way of kind of plotting the outliers. Not plotting, detecting the outliers. And also plotting, let's say. And statistical test assumptions, normality of residuals. We know for normality we use Shapiro-Wilk test, and again we get the residuals and we apply Shapiro to it. And homogeneity of variance, when you compare the variance, how homogeneous or how related or close they are, you use Levin's test right there on both. And then you use Shapiro. I think everything else is just a matter of printing. So let's go ahead and check this. Like I said, the actual code itself, nowadays in the world of large language models, anyone can do it. It's the knowledge that's very important. Which one should you use? And this code, as you can tell, parts of it, I used ChatGPT to enhance this. I'm like, okay, this is my base code. Can you actually put that in a nice way so my output report looks amazing? It tends to put like these emojis or whatever you want to call those icons, which is okay. I'm leaving them in, it's fine. So whenever you see this type of stuff in my code, you can clearly tell that, okay, I've used ChatGPT. I'm getting not just lazy. I want it to enhance, and I don't have the skills to find how to find the right emojis or icons. So why not ask? I use Claude, not ChatGPT, by the way, for debugging, and not for writing the entire code. Please tell me if you find any of these LLMs that actually do a good job in writing code that works 95% of the time. For the bare code, I kind of put together something, and then I ask Claude to enhance it, add print statements, add doc strings, and all that kind of stuff, which is cool. We live in 2025. Why not benefit from those, right? Okay, so ANOVA assumptions, we are checking all these assumptions right there, and I don't know what to talk about these, so there you go. Residuals homogeneity check, and yeah, so statistical test normality of residuals, they appear normally distributed. P is greater than 0.05 because it's 0.07 right there. Homogeneity of variance, Welch's ANOVA, it basically says variances appear unequal. It's not that unequal. I mean, visually looking at it, so I'm not super worried about it, but I'm gonna use ANOVA anyway. But if it's very different, even visually, then Welch's ANOVA would be the right one to use for you. 10 potential outliers is okay out of all of these data points, so we can drop those. We can include them if they're not very much outliers. Okay, so I mean, again, this is what Claude actually put together, assumption check summary. So it thinks that this is production code, but it's nice, it's cute. Okay, so now we are performing one-way ANOVA test, which is again very straightforward. ANOVA, it's directly, as you see, from the library, and I'm printing a whole bunch of stuff, basic information. For example, how many groups do we have? How much data do we have? Like how many data points, for example, and then what is the overall mean, and what is the group, statistics for each of these groups. Go ahead and print mean and variance and data for each of these groups, and then calculate total sum of squares. The reason why I did all of this in PowerPoint is it can get a bit confusing when you look at this here, but in PowerPoint I just did a few hand calculations, so you know what we are doing when we say total sum of squares and between the group sum of squares. I hope you know that by now. And this is amazing how Claude actually gave me this equation. I don't know how to type like squareds and all, especially this mean signature symbol. I'm feeling so accomplished by using Claude in enhancing the code, so I recommend that to others. Okay, step 3, calculate within the group sum of squares SSW. I followed exactly the same structure that I showed you in PowerPoint, except here I'm using Python libraries. That's the only difference, yeah? Not even Python libraries. I'm calculating in some cases by hand, like numpy.sum. Go ahead and keep adding it, so you get whatever you get, and that's the sum over there. So we're not calling, pre-existing libraries for some of these little tasks that we have in here. Okay, and F-statistic is nothing but MSB or MSW, so you get your F-statistic, and then we are calculating p-value. For that, I am using the stats.f.cdf right there, and then we are printing the p-value, and now we are calculating the effect size. All of this stuff we did literally as part of our PowerPoint presentation, so don't want to waste your time, except we are doing this on your actual data. Oh, actually, I forgot. The previous one was using a different library, and here I'm actually using the SciPy version of ANOVA. I don't think I'm using, because I'm using stats models ANOVA, I'm using SciPy ANOVA. I just wanted to compare both and see what's going on. I apologize if this is confusing, but if you find this interesting, go ahead and print both and then look at them. This is my way of learning how different these libraries are and what they are doing and so on, but ignore them. So I think I'm printing both anyway, so that's fine. So in this case, I calculated them by hand, by the way, right? I should have been clear, because the first one, I'm calculating them by hand right here, exactly the way we did in the PowerPoint. Sum of total sum of squares between sum of all this. In the other case, if you scroll down, I did SciPy ANOVA and then stats models ANOVA. I was just comparing how the values look like and all that. I don't know. I was going crazy. Sometimes I don't trust some third-party libraries, so I just want, or I don't trust my own calculations sometimes. So, okay. So let's go ahead and look at this. Number of groups 3, total size 333. After we dropped some of the null ones, and overall mean, and this is basically what we did hand calculated. Step 1, total sum of squares, between group sum of squares, and within group sum of squares. And originally I wanted to show you only this and not in PowerPoint, but again, this is not that straightforward, so I hope you appreciate what we have done. Mean squares, F-statistics, blah, blah, blah. Okay, all that fine. What did we get? At the end of the day, we got our F equals to 341.8949, because that's what F-statistic is, what we calculate, with a p-value of near 0. Okay, and these are the FX sizes. These are large FX. Between groups and all that, finally I printed out the table, and SciPy ANOVA, we got 340. Did I compare all these at the same? Yeah, there you go. So manual calculation from our own, we got 341.8949, SciPy 341.8949, stats model 34. This gives me a nice peace of mind. I don't know if you're as paranoid as me when it comes to these type of libraries, and especially when I code myself, I'm like, oh, what did I do? Did I do something wrong? And this is a nice validation. Awesome. I'm patting myself. Okay, now visualizing is, let's go ahead and run this. It's a whole bunch of different types of visualizations. And again, box plot, mean plots, 95% confidence intervals on the plots, and variance plot with the quartiles shown, and residuals versus the fitted plot, and a whole bunch of these plots. And again, I'm obsessed with these plots because you never know which one shows you the type of information you're looking for. And this is my favorite type of plot, actually. I don't like violent plots as much. I like these type of plots where you see the scattered distribution and then the ranges right there. Violent is okay. It shows you two distributions right there. Okay, I think not much to talk about here. And power analysis for ANOVA. Let's go ahead and do the power analysis. And we did this a couple of tutorials ago as part of the t-test. So please go back. If I repeat everything in every video gets very long, although nowadays each of these is like 45 minutes to 1 hour. But let's look at the important aspects right there. So eta square 0.6745, we manually calculated. I should have printed the manual one also here. And we achieved 100% power apparently, and greater than 80% to detect this effect size, and required total sample size for that is only 9. And required sample size per group is 3, but we have a lot more than that, right? So that's why we got near 100% power. If you have no clue what I talked about, you have to watch my video on t-test 2 videos ago, where I kind of talked about this power analysis to some extent. Okay, so 80% power line is right there. And at what sample size did you achieve 80% power? For a specific F value, for a specific Cohen's F value right there. Yeah, so that's what we are showing right there. Okay, and post-hoc testing, which so far we know that, okay, the groups are different, but visually we know that these two groups are different. This is important. Visually we know these two groups are different, these two groups are different, but are these two different, right? So which groups are actually different? That's exactly where it comes down to our post-hoc testing. Let's go ahead and perform the Tukey HSD, most powerful when sample sizes are equal. In our case, they're kind of equal, not really, but this is useful. And scroll down. Okay, so let's look at, oh God, target sign, great. ANOVA was significant with post ad hoc test. And what do we have here? Group 1, group 2, and if we're lower up. So here is Adderley chin strap different. We say reject is false. That means these two are, we cannot tell that these two are different. We can tell that this and Gen 2 are different. We can tell chin strap and Gen 2 are different. Of course they're different. We visually saw that, but we cannot tell that these two are different, which we know basically visually. So if you only care about visual analysis, fine, you're done. But if you want to quantify it, then these are the steps that you follow. You perform your ANOVA, and then you perform your, the Tukey's HSD post-hoc test to actually see which groups are actually different, and then and go ahead and report those values. And of course, if you're a researcher, scientist, if you have to probably report all of these mean differences between each group and mean differences between these, and go ahead and look at those. And I also did a plot right there to show that, hey, there's no difference between these, there is a difference between these. That's pretty much it. Okay, I've been talking for a long time. If you guys are still around, thank you very much. Let's end this video by looking at non-parametric, Kruskal-Wallis test, and just non-parametric alternative to ANOVA. If you're seriously concerned that, hey, you are violating a lot of these test rules for ANOVA, then this is the one that you can that you can use. And again, this is part of your stats.kruskal. I think stats and also the other library, they both SciPy, actually they both have similar tests. And also in the previous few minutes ago, we saw they both give identical results compared to and the match or manual. So a bit more confidence in those, and let's see how the final results actually look like. Again, no matter what test you pick, you have a test statistic and you have something like a p-value that tells you how to interpret your test statistic. Is it not how to interpret, but how the test statistic falls in in all the test statistic values that are possible, and if we need to reject the null hypothesis or not. Exactly same here. I can say Kruskal-Wallis H statistic is 212, means nothing. P-value is 0.000. That means everything, which means we believe that this is there is an effect right there, and the effect size is 0.6366 or eta squared. Again, I mentioned about eta squared in our PowerPoint presentation, so we can say there's a significant difference between the groups. We know that there's a significant difference between them, and here are the values. We got identical 3700 here, so these two are not different at all, and this one is different. So I don't know if you can say these are different. Oh, this is just body mass. Of course, you have to look at other metrics also. Yeah, and I just, again, this is the power of Claude or ChatGPT. I'm like, hey, just give me code for comprehensive results, and this is exactly what you're looking at. This just summarizes everything that we just had, and that's it. Just puts everything here at one place, so you get a nice summary right there. Okay, and I also asked, hey, if you are academic writing, what type of reporting should you have, and any guidelines on that basically. And it's been a while since I got out of academics. I do publish at least once a year, but I really don't know what these different guidelines are academics, and please validate these. Yeah, this is how, let's say this is one way of reporting your values. Let me put it that way. So these are completely generated by Claude or ChatGPT, that section. Okay, so the next one is correlation analysis. So we are going to look at correlation analysis in the next tutorial, and I seriously hope you come back. And in the meantime, hit the subscribe button. Thank you, and I'll see you next time.